Good morning. Thank you, Sabin, for accepting my invitation for this presentation. So we have 14 outstanding students from different parts of the country and the world, actually. We have a student from Switzerland, a student from Greece, student from China, and student from California, New York, Massachusetts, Connecticut, and different part of the country. So this is Frontiers programs in advanced modern physics. They are very enthusiastic to learn physics concepts. They are our future stars. Our speaker, Sabin Thapa, is originally from Nepal. He is doing PhD in nuclear physics, theoretical nuclear physics at Kent State University. So with that, I would like to request Sabin Thapa, could you please kindly present your research? Thank you so much.
Yes, thank you for the nice introduction, and thank you very much for inviting me, Dr. Kafle, and thank you everyone for joining the session. So I'll be mostly talking about my research, Quarkonia, proving the Big Bang on Earth. So I'm at Kent State. The research is funded by DOE and HEPT collaboration, and I'm associated with Center for Nuclear Research in Kent State. And I'm thankful to my advisors, Ramana Vogt and Andrew Hanlon. So if you don't know what Quarkonia are, then I'll guide you through. So here is the outline of my talk. I'll briefly give an introduction and motivation. So I'll talk how we can recreate the Big Bang conditions on Earth, and how we can probe the extreme conditions that we recreate in such collisions, and I'll give you some takeaways. So what happens when you heat or pressurize matter? For example, if you take liquid and cool it, you get solid ice, right? If you take liquid and boil it, you get gas vapor phase. And if you plot, different temperature and pressure and different states of water, you get phase diagram of water. And that gives you how different states or phases of water go from one to another state, right? So that's the phase diagram of water. But what happens when you want to see what's inside the water or what's inside the matter, what the matter is made up of? If you naively ask that question, then you will end up seeing possibly this periodic table, right? So everything in the universe, most of the matter in the universe is made up of these elements, right? These elements which we can detect using different techniques especially we use spectroscopic techniques, which uses quantum mechanical properties of atoms, different elements, right? So these elements can absorb photon and get excited, and also they can de-excite and release one characteristic wavelength of that element. So we can detect these particles, these elements in the nature by performing different spectroscopic techniques. These are kind of zooming lenses to see what's inside the matter, right? So what if we zoom in furthermore inside the atom? So that's done by scattering experiments. So physicists are crazy, right? If they want to see something, see the conscience or the makeup of something, they want to, throw really energetic particle in that matter and see what's in there. So um, so that was the early idea. So after the discovery of John Dalton's idea of indivisible atoms, J.J. Thomson discovered electrons, and he proposed this plum pudding model that I'll not describe in detail, right? So what are atoms? These are seas of electrons um, um, in the nuclear environment. That's what he observed when he tried to perform low energy experiment, right? So in 1913, Rutherford performed this alpha particle scattering experiment in the gold foil, and he discovered that there is something in the atom that is positively charged, and that's the positive nucleus of the atom. So he discovered nucleus in the atom. And Chadwick in 1932 discovered neutrons, completing the atomic nucleus. But these were, low energy scattering experiments. So what if we zoom in more? So that zooming in depends on how much energy we supply to that probe. So if the so energy is related to this quantity lambda. Lambda is the wavelength. So if there is high energy, means the wavelength is short. Meaning if the energy is low, if you hit some target with low energy scattering particles, then it can only resolve, atom like a point-like object, right? But if you increase the energy, then you can probe the internal structure of atoms, and you can see that these atoms are made up of protons and neutrons, but even these protons and neutrons are made up of individual these quarks and gluons bound together by strong nuclear force. So let's ask again, what are we made up of fundamentally? So if we ask that question, this answer is provided by standard model of particle physics that you must have seen multiple times in this talk series, right? So these particles on the left hand side, these matter particle or fermionic particles, on the right hand side, boson particles. So interaction of these matter and fermionic particles make up the visible universe, right? And so normal matter are made up by especially these light quarks and gluons. And these light quarks and gluons, you cannot find those freely in the nature under normal conditions. Why is that? Because they are confined by a strong nuclear force called quantum chromodynamics. So unlike the quantum electrodynamics, electrostatic force, which has Coulombic repulsion term, like this is the Coulomb term. So this is some charged particle, electrically charged particles experiencing each other's electric field. And you can see the electric field of charged particles extend outward, right? And that and the interaction between them is the Coulomb repulsive interaction if they are like charges, or Coulomb attractive if they are unlike charges. And um, if you pull those apart, like these electric charges apart, then the potential between them is decreased, right? Like the force of attraction between them is decreased, right? But that's not the case for two quarks. So two quarks uh, are interacting via strong nuclear force, and the strong nuclear force carrier is the gluon. And gluon has unique property, unlike the photons of electromagnetic force. So they are self-interacting, meaning the flux tubes, like gluon field, they don't extend outward. Instead, they make a flux of tubes called gluon flux. Why is that? Because the QCD forces have this linear scaling term in addition to this Coulombic term, and this linear scaling is responsible for the confinement. As you as you as you pull these quarks apart, the energy is stored in this gluon flux tube that increases linearly with this length or separation between the quarks. Like if you really pull those apart, then the energy will be so high that new quarks, anti-quarks will form, and that's why we cannot see free quarks in nature under normal conditions. Why? Because the force of the strong nuclear force is in the order of 1,000 newtons, thousands of newtons, that you can see the calculation. It's really strong compared to normal force. So that's why quarks and gluons are normally confined inside the hadrons, right? And quarks and gluons, they have color charge in addition to other quantum numbers. And that color charge that's why we call the theory quantum chromodynamics. And hadrons are color neutral, like they are not observed with color charge. They are always confined inside, like quarks and gluons are always confined inside the hadrons. And we can find protons and neutrons and lambda and other hadrons. Or we can also find hadrons made up of quark and antiquark called mesons. These three quarks combine to form baryons. And these are the normal hadrons we find in normal conditions. But what happens if we increase the temperature of matter, if we heat the matter at extreme conditions, right? So if we heat the matter at extreme conditions, you obtain um, plasma state. Like the electrons in the matter will be free to move, right? They make a soup of freely flying electrons, and that's the QED plasma. That's the core of the sun. Like if you increase the temperature to around million degrees Fahrenheit or degree Celsius, then you obtain an state of matter called plasma. That's present in the core of sun. But what if you increase the temperature to 10 to the power 12 kelvins, billion trillion kelvins? Then you obtain a exotic phase of matter in which these quarks and gluons that make up these protons, neutrons, and pions, normal hadron matter, they are deconfined. They are color ionized into these freely flying quarks and gluons, and that phase of matter is called quark gluon plasma. But why are we interested in this exotic phase? That's interesting question that I'll address later. So at really high temperature and at really high density, this baryonic density is the density of let's say normal hadronic matter. So if you increase the temperature and density, this normal hadronic matter, atomic nuclei, they change their phase to an exotic phase called quark gluon plasma, right? And these phases are present. You can study this phase of matter in different conditions, like in Large Hadron Collider or in relativistic heavy ion collider in Brookhaven National Lab. Also, like you can study these matters in the core of neutron stars where the density is really high. And there are so many questions that are not answered in this QCD phase, like critical point. We don't exactly know where the critical point is, among many other questions. So, where are these exotic phases of matter formed? So if you see the history of universe, if you go back 13.7 billion years ago, when there was no day or night, because there was no earth, right? So um the the universe started, 13.7 billion years ago after a big bang. And like shortly after the big bang, the temperatures or the density of nuclear matter was so high that there was an exotic phase of matter called quark gluon plasma formed shortly after it. And there are different experimental observations for the, for this, about the history of this universe. And one of the best is this map of the early universe, like obtained by NASA Wilkinson microwave anisotropy probe. And this is the history of early universe around 380 years ago. And this is the first afterglow of the Big Bang, right? Before this phase, the universe was completely opaque. Why? Because light could not propagate like freely. So in order to detect the like light, you have to be able to detect the in order to detect this matter in the universe, you have to be able to detect the light coming from that phase, right? That place. So this um, cosmic microwave background is the oldest light we can see, right? And that was discovered by these two gentlemen in Bell Lab who received the Nobel Prize. So these Big Bang matters can also be recreated on Earth. So in these large colliders, Large Hadron Collider situated in Switzerland. So you take two heavy nuclei or protons and accelerate them at the speed of light and smash those together, and we see what happens um, when we smash those together and detect those particles and infer different properties about different mechanisms, right? So this collision process can be illustrated by this picture. So in those collisions, you take two heavy nuclei and accelerate those at the speed of light. When those nuclei are accelerated to the speed of light, they they become flat, pancaked because of Lorentz contraction. And when they smash together, the, the temperature reaches so high, the density reaches so high that we can obtain the bunch of matter, including the QGB phase of matter, and that expands and cools down into different particles that we can detect in the detectors. And in the detector, we can detect less energetic or less heavy particles. We call them soft probes. We can also detect very heavy particles that are hard probes. I'll just discuss this Quarkonia, heavy quark particles that are detected in these detectors, and what we can infer or learn from those. So let me introduce what quarkonia are. So quarkonia are mesons. These are hadrons made up of heavy quarks. Bottom, top, and charm quark are the heavy quarks because they have really heavy mass, like in the range of several GeVs. And they can combine with their antiquark to form a bound state called meson. They have really hard scale, so they are not produced. They cannot be produced in normal conditions. So they are produced only in the hard collisions, and you can provide their explanation by using effective field theories. And there are two, like we are generally interested in studying about charmonium, the bound state of charm and anti-charm, and bottomonium, bound state of bottom and anti-bottom. And we can detect these particles in the experiments. So in the proton-proton collisions, there are, so you can detect, so if you plot the invariant mass of the decay products of these different Quarkonia states, you see these peaks in the event reconstruction plot, and these peaks are the different bottomonium states here. Like this, around 9.5 GeV is 1s state, around 10 GeV is 2s state, and around 10.11 GeV, like it's 3s states detected in proton-proton collision. But if you compare their yield in small collision, like proton-lead collision and lead-lead collisions, you can see like the red one is proton-proton, and this green in here is their yield in other collision system. Their yield is suppressed in proton-lead collision and lead-lead collisions compared to proton-proton collision. So the Quarkonia yield production is modified in heavy ion collision compared to small collision systems. And that is the signature of quark-gluon plasma formation. Why? So if you put these bound states of Quarkonia inside the hot QGP medium, these experiences color screening, like these color quarks and gluons in the QGP can obstruct or decrease the effective force between these bound state. And if the temperature is really high, then they can dissociate into unbound state. If the temperature is low, then they don't dissociate. And since these quarkonia come in different sizes and binding energies, the tightly bound states melt at really high temperature, and shallow bound states melt at low temperature. And this provides a thermometer, QGP thermometer. So you can guess, like you can estimate the temperature of QGP by studying different states, and that provides a QGP thermometer. So we want to model Quarkonia inside the QGP. For example, these are Quarkonia and this is QGP. QGP, the quarks and gluons are really hot, right? And these Quarkonia are moving inside the QGP, and we have to model those to predict their behavior or production patterns or modification in large collision systems compared to small collision system. And if those Quarkonia were classical objects, we would be able to use Newton's law, right? To see how they move in the quark-gluon plasma. But they are quantum objects, right? They follow Schrodinger equation, if you have seen this before. I included these equations mainly because maybe these will be interesting to you. So these quantum systems, like the description of evolution of quantum system can be done by Schrodinger equation. And if you don't know who Schrodinger is and who Dirac is, these two are two gentlemen who contributed significantly in the discovery of atomic theory. So they got Nobel Prize in 1933. So Schrödinger gave an equation that describes the evolution of quantum state in the universe, for example. But our quantum system is not that easy, right? So here Quarkonia are not alone. They are interacting with the environment. So quantum systems are not completely isolated, right? And this can be modeled using something called open quantum system. I wanted to share this approach because this is the formalism which you can use to model real quantum systems. Why? Because real quantum systems are not always isolated with their environment. They are not always completely, non-interacting with the environment. They interact with the environment even with tiny fluctuations, right? And this interaction causes to them to lose their quantumness. And we can model this using open quantum system. And I'll not describe all these equations, right? And we can make several assumptions to obtain the evolution dynamics of this system, bottomonium system in the quark gluon plasma, so that we can infer properties about this environment. And we are not directly studying this because this environment is really large, like it has so large degrees of freedoms. I'll just skip this. There are other effects the Quarkonia experiences in the QGP. And so if you try to model these Quarkonia systems using open quantum system, you obtain this quantum master equation. This gives the real-time evolution of real quantum systems that are not completely isolated with the environment. And this equation gives the evolution without, like, this term is the Schrödinger equation when there is no interaction. But because of the interaction, there are additional terms in the equation that encode the effect of the medium in this quantum system. And here, Quarkonia is just one example of quantum system. This equation can be used to model any systems, other systems. For example, qubits in the quantum computer can be modeled using this formalism, right? Why? And because the qubits are not always isolated, they experiences noise, and that's why we cannot perform, ideal quantum computation because of this interaction with the environment. And as a theorist, you have to predict the experimental observables from the theory. And one experimental observable is how modified the yield of these different states is in the large collision systems compared to the small proton-proton collision systems. And this modification can be quantified, right? And we can calculate that modification in for example, this is for lead-lead collisions. And we can either calculate, we can predict, we can get the results and compare those with the previous experimental observations, or we can also predict what how these observables will look like if they are not measured by experiments. That's what we can do theoretically, right? We can provide the predictions for the future experiments or explanations to the previous experiments. So with that, I'll conclude the talk. So ordinary matter hides its true colors, right? Color mean the color quantum number that quarks and gluons have. And quarks and gluons are always confined into hadrons to form colorless neutral particles, color neutral particles. But if you really provide extreme conditions, then this matter can melt into primordial soup that's formed shortly after Big Bang. And Quarkonia, quark and anti-quark pair, or tiny heavy quark atoms, they act as thermometers and spies inside this extreme plasma. And we can track different properties of these particles to uncover the properties of hottest matter ever created, and we can understand the glimpse of early universe through this um, um, study. And this study is particularly important because if you notice, cosmic microwave background radiation, that's the only oldest light we can observe, right? We cannot have direct observation beyond that point. And this heavy ion collision experiments are one of the indirect probes of this early universe. Thank you.
Thank you, Sabin, for a nice presentation. Before what I'm planning to do is there is a one I wanted to you to
Sorry if
clarify
the
something
talk
like
was
you
too
mentioned
technical.
that the particles during collision they move at a very high speed of light. That means you mean that the speed of they are very close to the speed of light, right?
Yes,
Yeah.
99.9999% close
Okay.
to.
Yeah. Thank you. So just I wanted to clarify to the students
Yeah.
that they no matter particles can move exactly at the speed of light, but they are very close to the speed of light.
Yeah.
Okay. So thank you so much. Now, to make the discussion more informal, I would like to stop recording and there might be some question from students. Okay.
Yeah.
So